Hello, my name is Kolton Andrus. I'm honored to be able to speak at the DevOps Enterprise Summit, London. Today I'm going to talk to you about how many nines of availability is the right number for your team, your organization. I like to begin by giving public examples of why this is important. As we've seen the shift to COVID and online systems being paramount over the last few months, we've seen an increase in load and stress on these systems, and as a result, we've seen more outages related to them. Whether it's Zoom, our ability to game online, or our ability to make online trades, our opportunity to interact with these businesses and our systems online is paramount, now more so than ever. Why are we seeing more of this failure? Well, the answer is a lot of the design decisions we've made over the last 10 and 15 years come at a cost. We've prioritized decoupling our systems. We've prioritized speed of innovation and being able to enable teams to move quickly. But with this has come a cost in complexity. No longer is the day that an architect can hold the entire system in their head. Now there's many, many moving pieces, and they're changing often, if not daily, hourly. What this results in is what I lovingly refer to as the microservice Death Star. These are examples from Amazon.com in 2009 and Netflix in 2012. And just looking at this picture illustrates the point. It's hard to comprehend it. It's hard to make sense of it. There's an inherent complexity in our systems now. This is the chaos that we have to deal with, the chaos that we're here to tame. The old world approach of testing is no longer sufficient. We used to focus primarily on our code, unit testing and integration testing, what we'd written. But in modern distributed systems, the dependencies that we take and their healthiness has a big impact on whether our system behaves correctly. The configuration needed to run a system within production is also paramount. The timeouts, the thread pools, the security groups, the auto scaling. Our infrastructure is more ephemeral, can come and go at any point. And our people and our processes are critical to being able to operate our systems well. Many engineers are now finding themselves as SREs or on call and may not have had the experience and the opportunity to practice operating these systems at scale. What we're seeing is a trade-off of this ability to move quickly that comes at the cost of reliability. And what we would really want is to be able to move quickly and maintain that reliability. To do that, we must shift the curve. We can't simply take the same approach that we have before. It requires a new way of thinking about things, a new approach. From my time as an engineer on call at Amazon and Netflix, and my time building and operating systems such as these, the best answer that I've found is chaos engineering. Now, chaos engineering means different things to different people. Some people believe it means we're going to randomly cause failures and see how the system and the people respond. And while there's truth to that, I think the definition that's best is around thoughtful, controlled experiments designed to reveal weakness in our system. Akin to the scientific method, we're going to go out and test a hypothesis. And because we're here to prevent outages and to build reliability, we're going to be very thoughtful about how to cause those failures so we don't inadvertently make things worse. Now, some people feel like this is a little counterintuitive. And when I'm home for the holidays or hanging out with my family, the vaccine analogy has been one of the best ways to explain this. Now, we're going to inject a little bit of harm into our systems, same way that we might inject a little bit of harm into our bodies. But this is so our systems and the people that operate them have an opportunity to respond, to learn, and to build an immunity to those types of failures. Once we've seen a failure and we've mastered it, we'll be much better prepared to handle the next failure. As I mentioned, we never want to cause a failure, we never want to cause an outage or customer pain as part of this. And so we're doing this by being thoughtful of what is the blast radius. What is the potential impact or side effect from an experiment that we're going to run? We always want to start with the smallest experiment that will teach us something. and slowly grow it as we build trust and confidence in our systems. We might begin in development or staging by testing against a single host or 3 hosts. And if we find a critical error, great. We've mitigated risk and we're able to fix it much earlier in the process. But if it behaves how we expect, we continue to scale that until we've tested all of our staging environment. When we're comfortable there, we're going to move into production, but we're going to reset that blast radius back down to the smallest piece, a single device, a single user, and then grow it again. It's important that we're testing both the small scale and the large scale. At the small scale, we might be catching a null pointer exception or a failure condition we haven't tested for. At the large scale, we're testing how our system handles duress. Do we shed load as appropriate? Do we back off of downstream dependencies? Do we have enough capacity to handle that influx when things begin to slow down or degrade? So I want to step back and give a little bit of context. As someone that served as a call leader or an incident commander for 10 years, I have a couple of tips and tricks about how to manage an incident and what's important when an incident occurs. First is, let's talk vernacular. Let's define some terms. First of all, we need a good metric to track customer health and behavior. At Netflix, we use stream starts per minute. At Amazon, we used orders per minute. This is some measure of, can the customers use our system and are they happy? Now, what happens when bad things occur? Well, we can break an incident into a couple of pieces. How long does it take us to understand that there's a serious impact? That's the time to detection. And this usually takes a couple of moments as we're comparing week over week data or we're